Hello, everyone. I want to use this video to go over our lecture number 4, coordinate systems. Let me share the screen with you. Right. Okay, so this lecture will be, I will say, the most challenging chapter or the lecture in the whole semester. So I want you to pay extra attention and study with me. So let's get started. So this lecture, we will focus on map projections and coordinate systems. You know, 4 aspects of geographic information. The number 1 important is location, right? So we want to understand how locations are defined on Earth's surface and also on maps, okay? So we are going to study those key concepts: geoid, ellipsoid, datum, map projections, and coordinate systems, okay? So they come one after another, okay? So you need to first understand the first set, and then the second and the third, okay? So let's get started with geoid. Here, just some jokes for our live lecture. Okay, so you can see, I think it's in 2019 or 18, President Donald Trump, he wanted to buy Denmark, but you can see on the map, he wanted to buy Greenland, but Greenland belongs to Denmark, right? So you can see on the map, if you put Greenland and Denmark side by side, you can see Greenland is larger than Denmark, right? So you can see here, well, you just need to buy Denmark, which is 1/5 the size of Greenland, and you can get a great deal, right? This is a joke, but let's play with this true size, and you can see on our maps, actually you have a lot of distortion, and this is one type of distortion called the aerial or size distortion. You can see on this map, actually, we exaggerate the size of Greenland a lot, okay? And here, actually, if you want to locate one location on the real Earth surface, it's really hard, including those famous online maps. And you can see the same location like Dodger Stadium, for example. On Google Map, you have this set of coordinates, latitude and longitude, right? But you can see if you check Bing Map, that is developed by Microsoft, you have different number. And here map, I think it's a Nokia version. You also have different number. OpenStreetMap, you have different number. Why? How comes, right? Okay, so here's the thing. When we want to locate one location on the real Earth surface, we need to set up X and Y, right? Longitude and latitude. That one actually is not unique. You don't just have one way to set up longitude and latitude. That depends on our first thing, geoid, ellipsoid, and the geoid and ellipsoid and data, okay? So there's another video I want to play with in our live meeting, but we do have a book. I have that in my office right here. Okay. How to lie with maps. Oh, it's hiding in my background, but how to lie with maps here. Put here, yes. How to lie with maps. Okay. So choose different geoid and map projection. Actually, it's one way to lie with maps. And from another perspective, never trust your maps 100%. Okay, because maps contains a lot of distortion. Okay. All right, so let's start from geoid. So what is geoid? Basically, that is the real shape of the Earth. So if I ask you the real shape of the Earth, people say it's round, it's a ball. Actually, it's not a ball. People call it's ugly potato. Actually, it's like a potato, and people name it as Potsdam gravity potato. Like here, it looks like this. based on 2014, December 15th. Based on the gravity distribution of the Earth's real shape actually is like this. Okay, it's like this. And you can see some part you have bulge right here, mostly at the equator. Okay, at the equator, we call that equatorial bulge because Earth orbit around its own axis. So you have this centrifugal force, right, to push the weight, okay, to the equator. And you can see the two poles a little bit compressed. So that is why later you have ellipsoid. Okay, let me go back here. Okay, so this is the real shape of the Earth. But you can see I put them on the real Earth surface. Geoid is like this, but our Earth's real, including terrain, the surface is like this. Okay, another way to call this geoid is mean sea level. So it's the same as mean sea level. So basically, we just consider gravity. Okay, but you can see here, well, it's really hard to define longitude and latitude on this ugly potato, right? It's irregular shape. So that is why we have this. The second concept after geoid is ellipsoid. So basically the idea is we want to use a mathematically perfect shape to approximate this ugly potato, the real shape of the Earth. Okay, so you can see here you have two options. You can use like more close, is closer to ugly potato, two poles get a little bit compressed. You can use this oval shape, or actually it should be called ellipsoid. Okay, or well, you have another option is just use a ball. Mathematically, it's easier to calculate, but it's a little bit less accurate compared to this ellipsoid. Okay. All right. So how much you flatten your two poles? Actually, you can measure that using this flattening factor. Okay. So you use this major axis, semi-major axis, that is a longer one from the Earth center to the equator. Okay, and the Earth center to the two poles. Okay, this is semi minor axis B. So you calculate how much you flatten it. Okay. So you can see we actually have a lot of versions of ellipsoid. Okay, why? Well, number one reason, different users. You can see here in the last column. Okay, so Great Britain versus Australia, they have different version, right? And also the Earth's gravity field distribution also change with year. You can see the one I showed you is in 2014. Well, that change every year, okay? And every several years, you need to modify your ellipsoid. So that is another reason, okay? So each version, you will have this major radius, equatorial radius, that's a longer one, polar radius, and your flattening surface, okay? All right, then, well, people say, oh, I have this ellipsoid. I revised it every a few years. I've done. No. After that, you need to consider, okay, I have this ball, and where is my starting point, right? How I match, how I put this ball, it's an approximation of the ugly potato, but how you fit this ideal shape to that ugly potato. Okay, how you fit this ideal shape to that ugly potato. Then that is the third concept. It's the reference point, or we call them datum. Okay, so with the ellipsoid, we still need to know how the ellipsoid is matched to geoid, ugly potato. Okay, and we need a set of points for which horizontal, latitude and longitude, and vertical positions are actually measured. Okay, so you basically to feed this ideal shape to the geoid. Okay, let me give you one example. So for example, here this shaded area, that is an ugly potato, okay? And you can see you actually can have different ways to fit this ugly potato, different ellipsoid with different data, different way to fit it, okay? And you can see here give you transaction view. Okay, you can see here, those are your reference point on the Earth. Okay, and you now I can see the Earth surface like this, or I can see the Earth surface like this, a solid line versus a dashed line. Okay, and those reference point actually you can see them on the Earth surface, actually including our campus, Santa Monica. You have a reference point on campus just to the north of our library. Okay, if you click on this link, you can type in your, let's see where it is. Let's see where it is. Interactive maps, yes. Okay, and okay, let's zoom into Santa Monica. Or I got that being here. Let's see. All right, so you can see we have those reference points, and you can see here in our college. See, we have this one, this is our library, right? You have this one, you also have this one, you also have this one, maybe in the cafeteria area. Okay, and you can see those are the classical horizontal reference. Okay, we don't have, oh, we do have a approximate height reference for both. Okay, right, we don't have GPS site. Okay, but if you zoom out, you can see those reference points. Okay, actually, it's clear. It's everywhere. You know it, across this country and also globally. Okay, so really interesting. Okay, you need the set of reference points to fit the ideal shape to the geoid. Okay, all right, so summary here. Datum including the reference points, but in many cases, we also combine the ellipsoid, the version of ellipsoid you choose, okay, to fit their surface in the datum. So in many GIS software, you don't see ellipsoid, okay, but you see datum, but datum contains ellipsoid, okay? So that is one note. We have two types of datum, okay? One is you can fit the Earth globally. You can fit the Earth globally. So basically, we try to minimize the offsets globally on average. Okay, so in which occasion you will need this, like GPS, like global positioning system, right? GPS. Well, you want the people on the Earth use this coordinate global positioning system. So you want to use the datum, reference point, and ellipsoid to globally approximate the ugly potato geoid, right? So in that case, we want to put the origin, the center at the Earth's mass center, okay? And then to fit the entire globe as much as possible, okay? And you do have local applications. So for example, you just want to make a map about your US. So you won't care about the offset between this geoid, between this ellipsoid and China. All right, so you can see here, we can actually have the origin on their surface, for example, right here. In that case, this part will have the minimum distortion, right? So your map, the measurement on your map will be more accurate. Okay, so we call that local data. Okay, so you can see, give you a few examples about global datum and local datum. This one is the most commonly used datum, global datum, WGS 1984. Remember, GPS, you said. Okay, from another angle, if you download the data, people say they're from GPS. Well, you immediately know the reference datum, ellipsoid, actually is WGS 1984. Okay, and you can see here, this is the ellipsoid reference of WGS 1984. Earlier, we do have a GRS 80, and you can see we do have a little bit difference here in the semi-minor axis. This is the early version of WGS 1984. Okay. And just give you another example, this just approximation, okay, or different datum, you have different measurements of longitude and latitude, okay. So you can see here, this is my GPS, and I put it on the line of Greenwich, England, okay, should be 0 degree latitude, right? But you can see my GPS, the vast reading is not 0. Okay, actually, if I want to make it 0, I need to move to the east almost more than 102 meters. Okay, why? Because the original Greenwich, England, that 0 latitude, 0 longitude, actually was set up based on the very old version and local version data. Okay, they're different. They're different. Okay, so here, local data. Okay, in US in 1960s, 70s, our old version of our geologic map. Okay, you can download from USGS. They actually use this data called North America data. It's 1927 version. Okay, it's a local data, and the origin actually is the geographic center of lower 48 states. It's in Kansas. Okay, and this is the measurement of A and B, the semi-major axis and the semi-minor axis. Okay, and you have about this many reference points across the US, just fit US. Okay, and later we do have this global version, okay, global version of the datum we adopt. This is the global datum, okay, North America datum 1983. It's a global datum because we want to feed our coordinate system into that GPS system, okay? So that is a global datum, okay? We want to feed the Earth entirely, okay? And it's close to we want to put the origin at the mass center of the Earth, okay? And earlier we choose this GRS 80, this ellipsoid, and we have more reference points to feed the global datum to the real Earth surface entirely, right? So you can see this is a difference between this NAD 1983 versus this local Clark, okay, this data, okay? And you can see, no joke, on our old version topographic map and the later version topographic map, you do have this difference, actually very big in some areas, okay? So in that case, if you have an older version topographic map, you want to transform it to the newer version, or you want to overlay the geographic features with the newer version, well, you need to convert your old NAD version to NAD 1983. Okay, so that is called datum transformation. Okay, later let me show you how to do that. All right, the datum we have been talking about by far, actually they are vertical data. They help you to define longitude and latitude. Horizontal datum. Here we talk vertical datum, basically how to set up our zero elevation. Okay, we call that vertical data. Okay, it's a base measurement point or set of points from which all the elevation are measured. Okay, so you can see we have this National Geodetic Vertical Datum 1929, and also have this North American Vertical Datum 1988. So our vertical datum also changed with years. Okay, but I do want you to here is how we measure it. Okay, how we geodetically measure those reference points and their elevation against those data. Okay, but here I want you to draw your attention here. Based on different version, different datum, we also based on different measurement, you do have different type of height. Okay, type of height. So for example, what is ellipsoidal datum? Well, that is from the ground, okay, the surface. You measure how far you are from your reference ellipsoid right here. Okay, that is your ellipsoidal height. Okay, but you can also use this plumb line, right? You have this plumb at this lead. It's very, very heavy, right? They are basically drawn by gravity, right? If you use that one, you actually measure this bigger uppercase height. We call that geoid, because remember, geoid is defined by gravity, right? So basically we have that, we call that metric height. They're different. So in other words, your height measured by your GPS is different from the height you measure, for example, based on this total station or tripods, this measurement. Okay, so you can see here the difference between those two, we call that geoidal height. That is the difference. That is the difference offset between your ellipsoid ideal shape and your ugly potato. Okay, so again, never trust your GPS, the height. Okay. All right. So, anyways, with that, you pick one data. Okay, the way you feed the Earth. Okay, you pick one ellipsoid and the way you feed the Earth, and you will have an ideal shape, right? And then on that ideal shape, you start defining your longitude and latitude. So that is why at the beginning of this lecture, you see Dodger Stadium, one location depends on which kind of ellipsoid datum you choose. You have different measurement. Okay, so here, based on the data, okay, a geographic coordinate system, longitude and latitude. Here, pay attention, is 3D. Okay, so we also call it GCS for short. Okay, GCS is a 3D coordinate system, geographic coordinate system, GCS. Okay, so then what is longitude and latitude? Here I need to throw you some terms, parallels and meridians. What's parallels? That is the circles that are the circles parallel to your equator. Okay, and then meridians are the semicircles connecting North Pole and South Pole. Okay, so you can see then how far you are from equator, which parallel line you are on, that is your latitude. Okay, the range is from from -90, that is the South Pole, to 0 equator, and then to +90, that is North Pole. Okay, and your meridians, that is a half circles. Okay, so you can see where our starting point is here, is the one past Greenwich, England. Okay, right here we define that is our starting point, 0 longitude. Okay, and how far you are from this we call prime meridian. Okay, prime meridian, that is your longitude. Okay, that is your longitude. You can see the value range is from -80, -180 to +180. Actually here, those two, they're same. Okay, that is the one passing in the middle of Pacific Ocean. Okay, but if you go to the left-hand side, that is our western hemisphere. If you're facing to the prime meridian, that is our western hemisphere. Then negative. If you go to the right-hand side, if you're facing to the prime meridian, that is your eastern hemisphere. That is positive. Okay. All right. So that is longitude and latitude. Okay, so here's a YouTube video to help you understand longitude and latitude. And here, in terms of longitude and latitude, you have two ways to present it. DMS stands for degree, minute, and second. Okay, so we use those sign to represent degree, that's a circle, minute is 1 prime, and second is 2 primes. Okay, and how to convert it? Well, 1 degree equals to 60 minutes, just like our clock. Okay, and 1 minute equals to 60 second. Okay, so here is a smaller unit, and you go bigger and bigger. Okay, and another way is decimal degree. Decimal degree. So basically, you convert those smaller unit back to degree. Okay, so basically, you first need to convert your second to minute by dividing this number by 60, and then you add them up. Okay, that's your minute, right? And then divide it again by 60, and you can convert it to degree. Okay, so here the same set of coordinates, and you have two ways to present it. Okay, on your map, Okay, but you don't have to calculate it by yourself. Okay, here is a converter. Okay, you can convert it, in either way. Okay. All right, then when you have longitude and latitude, remember longitude and latitude is defined on this globe, right? It's GCS, it's a 3D coordinate system, but most of the maps, actually all the maps, they're flat, right? Then how the coordinates on the map is defined? It's not longitude and latitude, by the way. It's a very weird number. Okay, before we dive into that part, how we define it, I want to remind you of this. How you defined your 2D coordinate system on a piece of paper, right? Like in your math class or geometry class. You need to set up X and Y, right? Then your X number measure how far you are from Y, and your Y number measure how far you are from X axis, right? The same thing. You also need this origin, right? The same thing when you define your coordinates on the 2D map, the same thing. You need to set up your 0. You need to set up where's my x-axis, where's my y-axis, and you measure how far you are from x-axis and y-axis, right? Okay, so here's the thing. First thing, we want to flatten our Earth. Okay, how to flatten our Earth? Through map projections. Okay, map projection is a systematic transformation to convert the 3D globe or your 3D measurement longitude and latitude into flattening surface. Okay, so here you need to consider 4 things. Okay, first, you need to consider so-called a developable surface or flattenable surface. Okay, so for example, here, a piece of paper is a flattenable surface, it's flat already, right? But this like a cone shape, you can also flatten it because you can cut it along this line, you can flatten it like a fan right here, right? And then the cylinder can also be flattened. So you can see here, I can cut it, okay, this way like a hot dog way, and then I can flatten it, right? Okay, then project aspects and light source location. So where you put this flattened paper on their surface, it could be at the pole, right? It could be somewhere, okay, some like a close to the equator, okay? How you tilted the aspects, right? Okay, and then here, think about when you have this surface, you also have a light bulb. You can turn on the light bulb to cast the shadow of your longitude and latitude to this surface. Then you get your 2D map, right, of all the longitude lines and latitude lines. Okay, this is the idea of map projection. Okay, but where you put this light bulb will determine what kind of the shadows of your longitude lines and latitude lines, right? So that is another thing you want to consider. And once you set it up, there is a standard line or points where you don't have shadow. For example, here, if I put it horizontally at the North Pole, the North Pole doesn't have the shadow if I place the light right here, right? Here, if I put here your cone, they will touch their surface along a circle, right? Then that is my standard parallel, okay? Though I don't have any shadow on that parallel. I don't have distortion on that parallel, right? And then, for example, this cylinder, I can touch the Earth at the equator, right? Then my equator doesn't have shadow. So that is called standard line. Okay. And again, when you flatten your developable surface, you need to define where is your x, where is your y, and the corresponding latitude and longitude. And then starting from there, you can define your x, your 2D coordinate system, right? So those are the components in your map projection. You will see that in your software. Okay, so actually I covered this already. You can see this is you use the cylinder to project our Earth. Okay, and you can see I put it like burrito way or hot dog way. Okay, around wrap up the Earth. Okay, and then I put in my light bulb right here in this case, and I turn on my light. I can see the shadow of all the continents, longitude and latitude. And you can see Greenland actually is huge because up there, it's very far away from my standard line, right? Equator in this case. And they have a very long shadow right here. Okay. And you can see here, that is a tangent way. I can also cut through. We call that second way. Okay, second along two lines. Then in that case, you have two standard lines instead of one. Okay, and then you can see this is a cylinder, conic way. We call that conic map projection. And this is my standard line. Okay, and here you don't have projection along this line. Okay, across maybe Texas, Florida. Okay, but when you're away from this standard line, you have a lot of distortion. Okay, and this one is just for like half of the Earth, northern hemisphere. You don't see southern hemisphere that much, right? Okay, so here I covered it. Let me go through it. It's called cylindrical map projection because your flattenable surface or developable surface is a cylinder. Okay, and this is called conic because your flattenable surface is like a cone. Okay, and this is your standard line. This one I use just a piece of paper flattened already. Okay, we call that planar map projection. Okay, but you can see you can put this planar map projection, this surface any place with any angle, right? And you can play with your light source. You have different type of planar map projection. Okay? And then here, remember on the projected coordinate system, on the projected map, well, you always have distortion, okay? And actually, this is the big dilemma in map making. Okay, all the projections introduce distortion to the resultant map, and you have two choices. You can make the shape preserved versus you can make the size preserved. Means you can keep the shape relative right, okay, to the real Earth surface, or the size ratio between different continents, for example, right at the real Earth surface. Okay, you cannot have both. No flat map can be both equal area or conformal equal area. That is, the size is preserved Conformal is shape is preserved. Okay, like in this case, this is UT, this is Mercator, transverse, this is Mercator. Earlier, the cylindrical map projection, but this one is another map projection. And you can see this is keep the shape true, but this one keep the size true. Okay, and just give you a few examples when you change the perspective, the angle where you place this cylinder, right? You can see the distortion basically change the shape of your continents also change. Okay, and this one play with the light source, play with the light source. Okay, and this one play with what kind of conic shape you have. Okay, all right. Then, like I said, when you flatten it in whatever way here you choose, okay, and you have a piece of paper, right? And then you can define your your X and Y 2D coordinate system. Okay, so let me summarize. Let me summarize here. We talk about longitude and latitude. They're GCS, they're 3D. Okay, you have that. Okay, you need to define your datum, right? Your ellipsoid and how you feed that ellipsoid. And then you apply a map projection, okay, to this GCS, to this ellipsoid. And then like this, cut the shadow, right? And then you can define your 2D coordinate system, or we call that projected coordinate system on this piece of paper. Okay, so from another angle to say that in other words, well, to define a projected coordinate system, you need two things. You need GCS, datum. You also need a way to project it, your map projection. So that is why on your in your GIS software, okay, for example, this is in Pro, you go to right click on a data layer, okay, you go to properties, you go to source, you can see spatial reference, and you can see here, okay, you can see here, let's see, this is your GCS, okay, GCS in this case, I have this one, okay, and you have the map projection, right? Okay, and then you can see this projected coordinate system is South America Albers equal area conic, right? So you can see I use the conic map projection. I preserve the size, not shape. Okay, and those two are my standard line. Okay, all right. Okay, so here actually you can change those standard line to let it pass your study area. In that case, you can minimize the distortion in your area. All right, and then how to select the appropriate map projection? There's no right answer. Okay, let me give you a tool called Projection Wizard. So if you go there, okay, you actually can drag a box to the study area you want to study. So for example, let's go to here because I really want to pass, I want to ship, okay, from the south tip of South America all the way to Antarctica, okay? And then I want to make my route across the ocean right here, okay? Then I want to maintain distance, right? Okay, and then here is your map projection. You want to use this one, equidistant conic, and these are your standard parallels, and this is your origin. Okay, so you can see this is very handy to choose the right map projection for your study area. Okay, so for example, I can also go to LA. I can zoom in a little bit close. Okay, so for LA, let's see, it's smaller. And move that here. So for example, okay, in this case, I want to make the shape true, and you can see transverse Mercator is your choice. Okay, and you need to set your central meridian here. Okay. All right. Okay, so this is a very useful tool to choose the right map projection in for your study area. Okay, and here, transverse Mercator. What's that? Well, here, that is a very important and commonly used coordinate system in many map making. Okay, so you can see basically I divide the Earth, the globe, into 60 zones. Okay, and each is 6-degree band of latitude, the longitude, excuse me. Okay, so for each stripe here, from here to here, that is 6 degrees. So you start from zone 1 is 180, okay, and zone 180 to the east, okay, that is, I'm sorry, to the west, that is 180 to 174. Okay, this is one stripe, and then the next stripe, that is the next stripe. Okay, and then for this is the other zones. Okay, so you can see this is zone 1 right here. Okay, the zone number. Okay, and also I divided into 2 halves, the northern part, UTM zone north, UTM zone south. Okay, and then you have for different latitude, you also can define your latitude. Okay, and here is how to set up when I apply this cylinder, apply this cylinder to this stripe. Actually, I don't want to feed this stripe like this vertically. I want to tilt it, that's called transverse Mercator. Okay, so you can see here, I cut through it, okay, to feed this stripe only. And you can see I have my 2 standard line. Okay, I also have my central meridian. It's called central meridian. Okay, it's not stripe primary, central meridian. Okay, and you can see here when I applied it, okay, those 2 standard line, no distortion. Okay, and this is your central meridian to define your starting point. Okay, and you can see here, use this central meridian. I can put my y right here, but convention, this is the convention. Okay, we don't want to use negative numbers, so we actually move this y 500,000 meter to the east of this central meridian. Okay, in that case, everything in this part, the northern part, okay, you have the positive numbers for your x and y. Okay, this is called false easting. False easting. Okay, in our case, actually here you can see that already. False easting for LA, right? 500,000 meters. Okay. All right, for the southern hemisphere, the same thing. Okay, we need to move the y to the east of our central meridian, but we also move x up to the equator. Okay, false northing. Because that false northing. So if I choose a location, for example, in southern hemisphere, let me go to southern hemisphere here. For example, let's go to Peru. For example, Lake Titicaca. Zoom out a little bit. Lake Titicaca, where are you? Oh, right here. Okay. Go here, here. Okay, I want to maintain the shape, and you can see false easting. Oh, here it doesn't show you the false northing, but you can see the x actually is right here at the equator. Okay, at the equator. Okay, and easting your starting longitude is right here. Okay, in that case, everything will be positive. Okay, so oh sorry, here I put my x below equator. I put my x below equator. Excuse me, let me roll back. Here, you put your x below the equator all the way. That's called false northing. Put your x this many meters south of the equator. In that case, everything will be positive. Okay, excuse me. All right, so this is from our textbook for one stripe, how you define your x and y. Okay. And this is another coordinate system we use a lot. We use a conic shape. Okay, it's a conic shape like this, And then we have two standard lines, okay, right here, okay, and we maintain, in this case, conformal as well, okay, and you can see here in between those two standard lines, you have distortion, and above it you also have your distortion, okay, but they have two different types of distortion. Let me show you, okay, because here in between your earth surface is longer, is this curved surface, right? You basically need to compress it. So basically in between those two standard line, your size is your size, yes, your size was your size is shrunk, okay, and beyond those two standard line, your size is exaggerated because you do need to flatten this surface, curve the surface to this part, right? So that is this about like 1/6. Okay, half is get 1/6 portion is get exaggerated and these get compressed. Okay, you also have false easting and false northing to make everything positive. Okay, and here is how you apply that one in United States, lower 48. Okay, so you can see here our standard lines right here. And in between all the states, their size got compressed, okay? And beyond that, like Michigan, Wisconsin, okay, they actually, this part get, oh, Minnesota actually get exaggerated, okay? All right, then how to convert between two PCS, okay? Two cases. If they have the same data, okay, well, you don't need to do that with datum conversion, okay? You just need to project the coordinate system back to the geographic longitude and latitude, and then apply your new projection again, okay? And if they define a different datum, you need to do this datum transformation, okay? In ArcPro or QGIS, you will see this if you have two different data, okay? All right, so try to avoid it because every time you convert it back and from one datum to another, you always introduce errors, okay, to your coordinates, okay? Avoid it. Here is the rest of the part of this lecture is different, a little bit different coordinate system, okay? This one is just for state. It's just for United States. Actually, we also use it a lot. It's called state plane coordinate system. So for example, if you just make a map for LA, right? You want to minimize the distortion in LA, okay? So your datum, your ellipsoid, you want to approximate LA as much as possible, right? So you can see that is different state. Actually, we have our best choice, okay? State coordinate system is you have different state. They cut the state into different zones, okay? For each zone, they choose the best way to fit that part of the state. Okay, so you can see each state either based on UTM, if they have this north-south elongated shape, okay, versus, for example, Tennessee, you have this east-west elongated shape. They choose different map projection method. Okay, in this case, we use UTM for California, but Tennessee, you will choose Lambert, that conic map projection. Okay. All right, so check your zone code for your location. That's also called FIPS code. FIPS code. For LA, older version, we have this 407, this code for Los Angeles, but later version, okay, in this NAD 1983, we just merged it to the larger 405 version, okay, 405 zone, this code. Okay. And you have another one. It's like a zip code. Okay, it's unlike state plane coordinate system or UTM. It's like a zip code. It's called Public Land Survey System, PLSS. Okay, it's a surveying method developed and used in US to divide the real property for sale and settling in the good old days. Okay, so basically you will see on your map, you have this township and range, those numbers. Okay, so basically we set up the baseline, okay, for each state. You can see here, those are the baseline. And from there, you measure every 6 miles by 6 miles. You divide your land into those squares and you code it. Okay, so here, this is the baseline. If you to the north, it's called township. Okay, and then if you go to the east or west, it's called range. Okay, and then you can see this will be township to S, to south, and range to W. Okay, so this is how you number, how to put an ID of each square. You can also further divide your 6 mile by 6 mile square into quarters. Okay, you will use northwest, southeast, so on to label it. Okay, so there's another way. So here, this one is a discrete, it's not continuous number. It's just like your zip code, right? For one area, you just have one number. Okay, so here, let me summarize the coordinate system we have been talking to by far. We have, in this lecture, we just studied this part. We studied the real coordinate system. Real world coordinate system means you can use those numbers to pinpoint a location on the Earth's surface. Okay, you can find that location, and you have different types of real world coordinates. You have your geographic coordinate system, GCS. It's a 3D. Okay, and then you apply a map projection to your GCS. Okay, but it depends. Your GCS also is, they are not just one number. Okay, it depends on what kind of datum and ellipsoid you choose, right? And then you apply your projection method. You can convert your 3D to 2D, right? That is your projected geographic coordinate system, or projected coordinate system is GCS, is 2D. You also have this discrete version like your zip code, like your PLSS, public land survey system, right? It just have a zone number basically. And in the following lecture, we are going to learn those so-called local or arbitrary coordinate system. What's that? That is defined by your computer or your scanner. Using that number, you cannot pinpoint a location on the Earth because it's defined by your browser, right? Or scanner, okay? So in that case, we need to translate this local or arbitrary coordinate system to the real world. We call that georeferencing. Okay, georeferencing. This is very useful when you try to put your scanned paper map, right, as an image to the real world surface, to put it in your GIS system. Okay, that's georeferencing. But we will cover that in our next lecture. Okay, so a few reference and online help I highly recommend to read and check out when you use it. Okay, so here in the live meeting, we may play with it to see the transition between different map projections. Okay, and this is your review questions. You must understand an answer for your quiz. Okay, all right. I think this is the last slide, and I hope you find it useful. Let me go back to summarize. Okay, so here, geoid, ugly potato. We use ellipsoid and datum to approximate it, right? Put that datum together, okay? And then you can define your longitude and latitude, 3D coordinate system. And then you apply map projection. You can convert that 3D globe to a 2D surface, and you can define your 2D coordinate system from there, okay? So you can see actually logic line is very simple, but here in the lecture have a lot of details. So I encourage you to watch this video multiple times, okay, to make it clear. It took me many years to make it clear. Okay, so here, take your time and really understand those concepts, because that's the foundation of GIS. Okay, your geographic information. All right, I'm looking forward to seeing you in our lecture, and bye for now.